Okay, everybody should be coming back for part B. I'm finished with the practice problem. Okay, so good. And we'll go over that when we get to class. Okay, so we're going to move right ahead. And we're going to be covering a new section, which is called piecewise multiple integration. Okay, what do we mean by piecewise multiple integration? Why do we need piecewise multiple integration? So, when we find the area enclosed by the curves that are not continuous, okay, catch the word, not continuous, then we have to break them up into by parts. Integration by parts is what it's called, okay? And so we have the area here that we would like to get for our x and for our y, dx, dy, and we're going to divide it up into area A1 and A2. We find here that we have two different areas enclosed, different areas. So we have x equals y and x equal to a minus y. And we have y equal to 2 plus x. And we have y equal to 2 minus x. So these are the areas that we need to concentrate on. But we got to remember we're doing dx area and dy. Very important. Okay. As we showed here, this one we will do area 1 and this one we'll do area 2. Okay, if the limits of integration are not continuous, which they are not, we need to split the integration into multiple parts. Okay, so the first one we're going to be looking at is our dx as it goes from where? As it goes from 0 to minus 1. And then we're going to be looking at y during that time frame. Y equals a minus x. And then my y equals 2 plus x. Then we're going to look at, we can call that area 1. Look at area 2. In reference to x is going from 0 to 1. And this is over the function that we have, which is y equals x, and the other function, which is 2 minus x. Okay, so the first one we like to look at on the left-hand side, we're going from 0 to minus 1. When we do that, we should have here this is 2 plus x minus a minus x dx. That'll leave us with dx. We're doing the dy first. Then when we come over to this one, we're doing the dy first. And so we'll get 2 minus x minus x dx. Okay, so now we'll go to another page. And we need to at least see where we started, where we stopped. This is where we stopped. Okay, so now we're going to break this down a little further. We have a minus x and a minus x that gives us, multiply these two together, minus times a minus is a plus, so we get a plus 2x. We have a minus x and a minus x, so we get a minus 2x here. Now, when we integrate, as we can see here, just looking at this one, okay, we're going from 0 to minus 1. We take the integral of 2, we get 2x. We take the integral of 2x, we get x squared. You can check this by taking the derivative of x squared, you get 2x. Take the derivative of 2x, you get 2. Okay, now we're going to add the other part, and this one we're going from 1 to 0. And if you take the integral of 2, you get 2x. If you take the integral of a minus 2x, you get a minus 2x. Take the derivative of this, and you know you get minus 2x. If you take the derivative of this, you can check yourself, you get 2. And we're going to be integrating them from these points. So we're going to plug in 0 for the first set. Okay, so that's 2x, 0 squared, that all goes out. We get a minus times 2 times the minus x plus minus x squared. Then we have this portion, and this time we plug in 1, 2 times 1 and 1 squared, and the other part goes to 0. So we see we have here, we get 2 for our area. So now you know how to do what? Multiple integration. Integration by parts. All right. Okay. So is the order of integration important? Very important thing. Does it matter which way that we go about this? Does the order matter? Okay, well, let's look at that for a moment. We have here, we can go from doing first in the parentheses the dy and then do the dx afterwards, or we can do the dx first and then do the dy afterwards. Okay? We will take a look at that to see if this is true. Okay, so we're going to let C, does A1 equal A2? So we have A1 here, and so we just have an f of x equal 1. That's all that it's going to equal to, 1, so that when we integrate, we can find out what these are. Okay, so when we take the first one, and we integrate, the first thing we notice here is that the first thing we do is dy, we get what? Y. Okay, so since all we get is y, and this is going to be 0, then we'll plug in hb divided by x. And now all we have is what left is the dx portion. Now we're going to integrate this in reference to x. So we get x squared divided by 1/2. And we're going to go from the points what? 0, from b to 0. And what we get here is that we have h 2b is a constant, and we have x b squared, and the b's can cancel, and we just get a b on the top, the square, so we get 1/2 base times height. That is the formula that we know. Okay, so now let's do it another way. Okay, we're going to find the area for 2. So we're going to do the x first, reference to our dx first, and then we'll come and do our dy. So when we first start this, the first thing we would like to do is be able to take the integral of this, which is 1 we start off with, so dx is just going to be x, okay? And then we have to look at x as it relates to b and x, okay? So we have bhy is our lower limit, and b is our high limit, upper limit, as we would call. So we plug in b minus b divided by h times y. Okay, now we're going to take the we're going to integrate in reference to dy, okay, the y component. So the integration of b is going to be by. The integration of b over h is going to be y squared and 1/2. So now we're going to plug this in, and we're going to plug in for these limits. Okay, so if we plug in at h, we get bh minus bh squared divided by 2h. And the rest of this goes to 0. So then if we subtract the 2, 1/2 of bh, we get, wow, wonderful, 1/2 bh. So that means what? So A1 and A2 doesn't matter. What order you do it in? Excellent. Order of integration. To evaluate, we are so glad. Okay, so when we evaluate this, okay, to evaluate, if we're doing dx, then we're doing our dy as we go from A to B for this area. Then we do the same thing on this side. Okay, as you can see, we're taking it first in reference to dy. So we have dy and we have dx. So as you can see here, that this one, that we do what's in the integration first, which is the y, which is the x portion, the dx, and then we come here and we do the y portion, dy. And we found out that the order doesn't matter. But what we would like to do, always remember the outer integral limit should be constant. Okay, the outer one, which is out here, usually. And then what do? Then we do the inner one first. And the limit will follow the function of the outer variables. So we always do what's in here first, what's closest together, and then do the other last. So now that you know how to do all of these, you should be able to, we'll give you some practice problems, and we'll finish off the rest in class. So you have this one, find the mass of a thin sheet shown below. Okay, that should be simple enough for you. Okay, use the integration, okay, two derivatives of z dx, dy dx to find the volume above the rectangular with vertexes at 0, 0, 1, 0, 0, 2, and 1, 2, and below the plane z at 8 minus 2x minus y. So let me give you a fourth problem, okay? In signal processing, the joint probability density function, f at x, y, of two random variables, x and y, and their joint cumulative distribution function, f at xy, are related by the integral. F of xy, f xx, as y goes to infinity, negative infinity, and x goes to negative infinity, we have f at xy, u, v, and du, dv. So instead of using dx, dy, we're using du, dv. Okay, that shouldn't be difficult. Given the random variables, which are jointly distributed according to these parameters, okay, f at x at u, v, where e to the minus the quantity u plus v, as v, as u is greater than 0, and as v is greater than or equal to 0, and is 0 any other time, okay, when u is less than 0, when v is less than 0. Please find f at xy. All right, you should be enjoying this. We're glad that everyone had a chance to be part of this, so we will look for you to be able to do all of these problems, and we'll look for you in class. All right, enjoy your day.